Hello, good morning, everyone. So today we are going to continue with the lecture on topological data analysis on part 2. Okay, so part 2 would be on persistent homology. Okay, let's begin. Okay, so this is the content of our whole course. So we are at semi-supervised machine learning called topological data analysis, and we did part 1 part last week, and then now we are going to do part 2 today. Okay, so the content of the lesson today, first of course, I'm going to introduce persistent homology. Before I introduce, I'll give you a little bit on the motivation of persistent homology. And then I'm going to talk about shape quantification with topological invariance. So shape quantification, remember the topological data analysis, especially persistent homology, we want to extract the shapes information. So what exactly information that we are going to construct? So we will look at topological invariance. Next, with a given point cloud, you have your data set in the form of a tabular form or a table. So we are going to construct simplicity complex at various levels. Okay, and then from this various level of simplicity complex, we're going to compute homology computation. So homology computation has got to do with shape quantification, which we will look at later. And finally, we will look at the Python package where we can run persistent homology and do machine learning. Okay, so that would be the content of this talk. Okay, you have seen this picture now, right? So persistent topological data analysis has two machinery. The first part will be a mapper algorithm where given a point cloud in this form, and this point cloud can be in any dimensional space, the output of a mapper algorithm would be a graph or a network. Okay, so it's a simplified version of your data where you get to see the structure of your data, the relation between the data set itself. Okay, so that's the first part. The second part here that I'm going to cover today would be persistent homology. So given data set, you're going to push into persistent homology machinery, which is the second part here. You would obtain a persistence diagram. Okay, this is a persistent diagram. This is an example of an output of a persistent homology, where from this persistent diagram, you would be able to use this feature here, so-called space, so-called shape information. Remember shapes information of the point cloud, and it's represented as a persistent diagram, and then we can vectorize the persistence diagram and then use it as a feature vector for machine learning purpose. Okay, so we will look at it in detail. But to tell you like a short, small story would be, look at this this hole here. Yeah, there's a two holes actually. One is that a big hole, and then the other one would be a smaller hole, which is this one here. So the smaller hole is encoded in persistent diagram, and the corresponding point is this point here, whereas the big hole is encoded by this point here. So the 2 points. So basically, the further they are from this diagonal line, the more prominent they are. The more prominent the hole is. Okay, right. So that is the blue points. Whereas the straight points represents connected component. Right. So the points that is in blue represents one-dimensional hole. Yeah, that's the hole that you see here. The big ones corresponds with this blue one, and then the orange corresponds to this point here, right? So the ones that closer to diagonal line, this points, are actually small holes that exist in your data set. It's one-dimensional hole, yeah, small one-dimensional hole. Anyway, that is a small short story, but we will look at it in detail in the slides to come. So today's lesson, would be twofold. First is to understand the principle of shape quantification in topology. Okay, so we are so used to geometry and Euclidean space, so we are going to look at a little bit on topology and shape quantification in this domain. And the second one would be we want to compute homology classes, which actually the reach information of the shape of the point cloud using Python package. And then once you have this information, shapes information, you're going to represent it in the form of a vector feature, so-called feature vector, and then we will use it for machine learning. So rather directly using data set, straight away you push it into machine learning model development, you will first do so-called feature extraction or feature engineering from a persistent homology algorithm, and then you will push it to machine learning model development. So that would be the lesson for today. All right, so okay, we have seen this actually. Okay, now let's look at the whole theme. So I have shown, and I'll show again. The theme is data has shape, shape has meaning. So that is the whole idea of topological data analysis. In fact, just recently in 2019, it was found that topological data analysis, the machinery persistent homology specifically, not just encode topological information of the data. Rather, it also captures the geometrical information of the data. Okay, right. Okay, so the first part, okay, so you have your question that you want to figure out, and so based on the question, you collect your data, and then of course you clean your data. Once you clean your data, you might want to do EDA, exploratory data analysis with mapper, in which by constructing a mapper graph of your data, you would be able to see the shape and structure of your data, and you would be able to elucidate the data's pattern, how it is like clustered and etc. So that is the first part that we saw in the previous lecture. So today, so once you have cleaned your data, once you have cleaned your data, it will be two ways actually. Yeah, once you have cleaned your data, so you're going to push into persistent homology. You're going to feature engineer. Yeah, you're going to extract the shapes information, and this would be your feature vector representing your data, and then you will do the train and test split and push it into machine learning method here. Of course, for training, you will use the training data set. For testing, you will use the testing data set, which we have splitted from so-called feature engineers here, feature engineered vectors. Right, so the rest is the same thing. Then once you have a model, you are happy with the prediction accuracy, then you push it for deployment and then performance monitoring. And then in any case, if you want to refine it, make a newer version of it, you might want to introduce a new model, collection of new data, and etc. So this is the life cycle which involves persistent homology and also mapper algorithm in data science. Okay. Now, a little bit on persistent homology. So for example, Gunnar Carlson, one of the so-called co-founder of persistent homology and also mapper algorithm. So his group, they're using for big data analytics, they're using for social network analysis, they're also using for medical science, finance, and etc. Okay, whereas this group here, Jose Piria, for his PhD, he tried to come up with different theorems and definitions and ideas on processing time series data set using topology, persistent homology. Similarly, Elizabeth Munch and her team from Michigan State University, they're using they always use time series data set with either persistent homology or mapper algorithm. Whereas Chris Straley from Ursinus College, US as well. He also does persistent homology, also mapper algorithm uh, using time series data set. In fact, he has done mapper algorithm for songs. He will take a song as an input and push it into mapper algorithm. Then he would create a mapper algorithm for a given song. Even they have done it for video. Yeah, for video, like a short video, you'll push into mapper algorithm and create a mapper graph for a given video. Okay, right. So next is Robert Rees. He's actually algebraic topologist. So he does a lot of pure part of persistent homology, and he has also done application for network flow and sensor network analysis. So he's from University of Pennsylvania. Whereas in Japan, a famous professor, Yasuoki Hiraoka, he does a lot of work on material science using persistent homology. Okay, so this is I would say this is like a little bit outdated. So there are many more domain using persistent homology and also mapper algorithm to create models or to do investigation further so that they can do a well-informed decision. Okay, so let's look at an example, right? So let's look at a scenario. Let's say you have a point cloud A in a two-dimensional space and X and Y. This is X, one feature, Y is another feature. This is how the point cloud looks like. Okay, that is point cloud A. And then you have another point cloud B, which looks like this. Yeah, of course, in the same two-dimensional space, this is how it looks like. And then you have point cloud C. Okay, so the question would be, as we compare a point cloud C to point cloud B and A, would you cluster point cloud C in point cloud B or point cloud A, which means point cloud C is similar to point cloud B or similar to point cloud A? So that is the question that we are going to answer now. What do you think? So if you look at the hole here, there's like somewhat like a small hole exists here, and there's also like a hole exists here, or you can also say like a big hole exists here, right? But there is no hole for point cloud A. So most likely, right? Most likely we would say point cloud C is homeomorphic. Yeah, the word homeomorphic, let's hold on to it. I'll explain it to you later, which is somewhat similar. In a very rough word, we'll say point cloud C looks somewhat similar to point cloud B, right? So here, the way we do it is that we looked at the whole. Yeah, so in a general setting, we need a good shape descriptor. Yeah, let's say f. We need a f, a function, or a transformer, or a or a or a mapper, or a map, which would take point cloud is a data set actually, which would map to any dimension, maybe a one-dimensional space. Like example, this has got two holes, this has got one hole. This information of 2 and 1, and this one got 0 hole, in fact, is the one-dimensional space vector. Okay, so a good shape descriptor would take in given data set, and it will give you the information of the shape in a nice array. Okay, so that array can be in any dimensional space, right? So this is the array that we are going to use. Actually, it's a feature vector, right? What type of feature vector? Is actually shape feature vector that we are going to use for machine learning tasks. Okay, rather than directly using the point cloud itself, rather we do a pre-processing and extract feature vector and then use it for machine learning tasks. So the idea is, again, that is called feature engineering. Yeah, you're extracting something out of your data set and using it as a feature vector for machine learning tasks. All right. Next. Now, the study of topology. So let's go a little bit on topology, to understand how we can quantify the shapes. Okay. So basically, the study of topology is all about connectivity, right? It's all about connectivity. So one keyword that's important when it comes to topology is homeomorphism. Yeah, homeomorphism. So we want to compare two shapes. These two shapes, is it similar or not similar? Rather, you're using the word similar or not similar, we'll use the word called homeomorphism. Okay, so What homeomorphism simply means, shape can be deformed into each other without cutting or gluing. Okay, so for example, right? For example, let's take a ball, like a plasticine ball, right? Plasticine ball where you can squeeze, make like an ellipsoid shape. So this is in fact was a sphere, filled sphere, right? You can squeeze it and make it into ellipsoid, right? So now it became ellipsoid. You can squeeze it. So you did not do any kind of cutting or gluing or poking, making a whole new hole. You're not allowed to do that. So we say the sphere is homeomorphic to ellipsoid. Yeah. So maybe this ellipsoid, you squeeze it such a way that the ellipsoid is not so elegant. So again, this sphere is homeomorphic to this crooked ellipsoid. So you can still say that. Okay, so that is the word homeomorphic means. Now let's look at a cup, yeah, coffee cup, right? So this coffee cup is homeomorphic to a torus. Yeah, this is a filled torus. Okay, so what it means, see there's a hole here, there's a handle has a hole, so that hole is actually encodes or reflects this hole, this big hole here. Okay, that is so a coffee cup is homeomorphic to a donut, rather than saying it's torus. I would say, okay, so you eat a donut with coffee, all right? Okay, so maybe I mean, due to some reason the donut is crooked, so this coffee cup again is homeomorphic to this crooked donut, right? Why? Because there's only one hole. So how about the hole that holds the coffee? That hole is not, it's not true. Yeah, it's not true. That hole is like closed hole. It's not really a hole. You can seize the whole thing, squeeze the whole body of the coffee cup and make it into the shape, right? So are you allowed to squeeze? Yeah, you're allowed to even pull out, right? But you should not cut it through. You should not add or glue something extra on top of it. Okay, so that is homeomorphism. Whereas we see here this sign here, right? This is not homeomorphic. A sphere is not homeomorphic to a donut. Why? A sphere has no hole actually, whereas a donut has a hole, right? So you get the idea of homeomorphic. So in mathematics, homeomorphic has two conditions. First, it is continuous bijective map. So between, for example, x and y, so for every element in x, there is a map to y. Yeah. Similarly, it has a continuous inverse map, which means from y I would be able to go to x, where y's element elegantly matches or maps to x, right? Whereas you see this function yx here, right? So if I go from x and then I have y, that's good, that's nice. So it has a map. Whereas if I go from inverse, right? So for example, if I take y, so y value of at some value here, and then y value at here, y value here. So at one y value, I have three x values. At one type of y value, y star, I have x1, I have x2, and I have x3. So there are three values for one particular y, which is not one-to-one, right? So that is why this is not homeomorphic. This function yx is not homeomorphic. So if you can you think of a function which is homeomorphic? All those monotonic functions are homeomorphic, right? Okay. Right. So we understand the keyword homeomorphism means, right? So the topology is the idea of the topology is again just like we say two objects are homeomorphic if they satisfy these two conditions. All right. Okay. So let's compare now topology and geometry. When it comes to geometry, things are very strict. We have a very strict rule, right? It's called rigid transformation, right? For example, we use, rather than using homeomorphic, the word homeomorphic, we use congruence. The triangle A is congruent triangle B if the length of each side, the angle of each angle, and the area is preserved, right? So for example, A, B, and C are congruent to each other, okay? Why? Because of length and angle and area. So very strict, right? Whereas if you look at in the second row here, triangle, say D, E, F, and G are not congruent, right? Not congruent. Because why? They do not have similar length or angle or area, okay? Whereas we can also, in the context of geometry, we also look at number of sides. The hashtag here represents number of, yeah, number of. There's a short form here actually, number of sides. So based on the number of sides, we can classify polygons. For example, all these are triangles, and we have like if I have 4 sides, yeah, different shapes. We say all that are rectangles. Okay, so when we talk about more general content, the general setting, you look at the overall shape of it. Now you're moving actually towards topology, right? So when you look at the general setting, for example, number of sites, it's more like encoding topology of your data. So whereas if you look at the local property, for example, the angle and the length, you are looking at the local property of your shape of your data, then it's considered as geometry. Okay, so for topology, for example, triangle A, triangle B, or even 1, 2, 3, 4, 5, 6. So hexagon, right? Hexagon C, and 1, 2, 3, 4, 5, some sort of polygon with 5 sides, right? D are all considered similar. Okay, all considered similar. Rather than using the word similar, a more accurate word would be homeomorphic. Okay, homeomorphic, right? So why? You can think of like squeezing and pulling, right? So you can always like squeeze it in such a way that you make this triangle, or you can like pull it and then reshape it and make it this triangle, or you can not triangle actually, and this polygon, or next the following polygon, polygon D. So you can always like push it and pull it and then reframe it, right? Right. So it's all homeomorphic. Whereas this triangle here, which is filled, right, filled, closed, there's no hole, is not homeomorphic to the triangle to the next to it. For example, let's say this is E and F. So E is not homeomorphic to F. F is homeomorphic to G. Why? This hole here, as you can see, this hole is preserved, right? So you can squeeze this so-called this content here such a way that it becomes like F, right? You can squeeze the so-called the width of the G such a way that it becomes F. So you can always do that. But G is, okay, let's say this is H, the final object is H. So G is not homeomorphic to H. Why? Because H has 3 holes. Okay, 1, 2, 3. Whereas G has only 1 hole. Right. So if you want to make G into H, you got to make 2 more holes, which now you are going against the rule of homeomorphism, right? So whereas on top here, the first row, all these polygons, you can see all of them, they have only 1 hole, right? 1 hole. Okay, so that's the difference between topology and geometry. So if you can roughly say topology is like, it's all about number of holes actually. Okay, the hole can be in any dimension. So this, whether the hole that we looked at so far will be whole dimensional one, a one-dimensional hole, right? Whereas geometry, we look at uh, locally. We look at the shapes information locally, the length, the angle, the area. Whereas topology, global shape, the global shape here that we have discussed so far, it's all about holes, one-dimensional hole. Okay, so that is what differentiates between topology and geometry. Again, the story, the whole domain of topology is about comparing 2 shapes. Are they similar or not? right? We want to find a metric, find a way to quantify the shape, the context of the overall shape of a given data set in our setting. Okay. All right. Now let's go further in. Okay, so there's one thing called Euler characteristic, right? It's a metric, Euler characteristic. It's a topological invariant, a way to quantify shape, right? So let P be a polyhedron with V vertices, E edges, and F faces. Then we define Euler characteristic to be the alternating sum of its building block. How I can make polyhedron? I can make polyhedron within vertices, using edges and faces. Okay, faces are means all the closed ones. If it is closed, we call it as face. Okay. Now, so the notation here, this notation represents Euler characteristics. The Greek notation, Euler characteristic. Okay, and so for Euler characteristic given polyhedron, it is the alternating sum. Alternating sum means plus minus plus. Okay, that is the alternating sum of the building block. For example, the Euler characteristic for a given cube is it has got 8 vertices, it has got 12 edges, and it has got 6 faces. Okay, 6 faces. All these are actually colored, but I did not color here so that you can get to see it. Okay, same thing for uh, uh, a tetrahedron, and then there's a hollow cube. So collection of vertices minus collection of edges plus collection of faces. Same goes here as well, hollow cube. So we get to encode now. We get to encode its Euler characteristic. So Euler characteristic is again computed based on the alternating sum of its building block, which is vertices, edges, and faces. So we get one number. This one number represents the shapes information. When the shape is similar, for example, if you take the cube, you maybe enlarge it like that, yeah, maybe expand at one part, it's still the Euler characteristic does not change. Okay, it won't change. Okay, so for example, and if you compare these two, tetrahedron and cube, it is homeomorphic because why? The Euler characteristic is similar. Yeah, you see, Euler characteristic is 2 for a cube. The Euler characteristic is also 2 for a tetrahedron. Whereas the Euler characteristic for a hollow cube is 0 because there's a, of course, obviously there's a hole in between which passes through. In fact, it looks somewhat similar to a donut. Okay. All right. So what it means is that this number, using this number, we would be able to differentiate between two objects, yeah, two shapes. Okay. So more examples on Euler characteristics. Okay, so for example, Euler characteristic for a point is 1. Euler characteristic for a circle, yeah, for a circle is 0. Euler characteristic for a sphere is 2. Right? For example, the sphere that you saw earlier, I mean, the cube that you saw earlier is closed cube, yeah, it's similar to sphere. Euler characteristic for a annulus, yeah, for like annulus is the shape of your CD, is 0, which is similar to a circle, right? So you can see Euler characteristic for a donut, like I should say torus, is actually 0 too. So you can actually see the one that has one hole, the object which has one hole has similar Euler characteristic. Yeah, and if it is closed, like a solid ball, it will be 2. Okay, it will be 2, but not solid ball. Sphere is actually a hollow, right? Sphere is hollow. Inside, like a ball, inside you have air, so it's 2. The one that you saw earlier, the cube, it's actually hollow inside. Yeah, it's 2. If it is filled, you'll get a different number altogether, which would be, I think, 1. Right? Again, you can always calculate. Okay. right? And so these are the shapes. So even though there are some sort of different shapes, somewhat different shape, but in general, there's one hole between circle and annulus and torus. The color characteristics is the same. So we can also go further, a little bit further, and look at Betti numbers. Okay, Betti numbers. What is a Betti number? So Betti number, the kth Betti number, we encode with a Greek letter uh, beta, Betti number. So the Betti number, kth Betti number of a given data set X refers to the number of k-dimensional holes in X. So for example, Betti 0 represents number of connected component. With the first one, Betti 0 does not really encode holes, whereas the rest, Betti 1 is the number of circular holes, so one-dimensional hole. Betti 2, this should be Betti 2, there's a typo there. The two-dimensional hole, yeah, two-dimensional hole. And you can go up to any number of Betti, yeah, because your data can be in any number of dimensional space, right? So we can calculate, compute up to Betti k of your data set. Okay, so let's look at some examples. So for example, you have a line. A line has just one component. So Betti 0 is 1. The line has no holes, no one-dimensional holes. So Betti 1 is 0. Whereas if you take, like, for example, three disk, yeah, three filled disk, yeah, three disk. This in topology we call this disk because there is no hole. If there is a hole, then we call it as annulus. This is annulus, and whereas this is three disks, we have three different shapes of disks. So we have three connected component, one component, second component, and the third component. So even though it's written as connected component, not necessarily it will be connected. Yeah, it's basically they are connected to themselves. So all these groups are connected to themselves, to themselves, to themselves. So we have three connected components. Are there any holes? No hole at all. So whereas for a circle, you just saw, so there's only one hole, so there's one, Betti 1 is 1. There's one connected component as it is. They are all the points are connected as a circle, so it's 1. And annulus is similar to circle, one connected component, and then there's one hole, Betti 1 is 1. Right, so for a graph, for example, this graph, this is a network. It has two connected components. So two connected component. How many holes? So one hole here, another hole here, and then another hole here. So there are three holes and two connected component. Whereas for torus, of course, it is one connected component. How many holes? There are actually two holes. One hole is like surrounding itself. Another hole is surrounding here. So two holes actually. And then, of course, Betti 2. Betti 2 would be two-dimensional hole. So this torus here, inside, just like a sphere, inside there's hollow, right? That is the one that's two-dimensional hole. A sphere, a ball that you play, inside there is just air. So that is the two-dimensional hole actually we are talking about when it comes to Betti 2. Okay. Okay, so the idea can be for Betti 1, it's nice the way to compute Betti 1 actually. What it means is that you can play with the idea of physically cutting the object and see how many times you can cut such a way that you will not make it into two. For example, if you take this circle, let's say this is a string made of a circle, you can cut once and the circle will become a line like that. Yeah. So it did not break into two pieces, right? So it was still intact as one. So that means you get to cut only once. So the number of cut that you can make will represent Betti 1. For example, let's see this ribbon, a twisted ribbon. A twisted ribbon is in fact homeomorphic to a Mobius strip. One connector bit. So it would, how many times you can cut? Still, you can cut only once actually, just like a circle. Like there, circle has one cut. So Betti 1 also, for Betti 1 for a Mobius strip is also one. How many times you can cut this through? Right? So there's no Betti 1 actually. There's no one-dimensional hole. Whether there is one sphere, right? One sphere. While Betti 2 is 1. Because why? There's one dimensional, or you can make one poke like that, one poke. If you make one poke, it become one piece. Like, for example, like you cut through here. Yeah, you cut or you make one poke. So if you make one poke, you can like strip it out and make a plane. Yeah, a plane. So just you made one poke, which goes through that face. Yeah, so that's why it's Betty 2 is 1. There is no Betty 1. There's no one-dimensional hole here. Okay. So for a torus, I said Betty 1 is 2, right? So you get to see, like, you can get cut through once. You can cut through all around here and then open it up once. So now it becomes like a plane. You can always squeeze it and make a plane out of this. So you get to cut once and twice. So that is why Betty 1 is 2. So the idea is, or what I'm saying is that, like for Betty 1, it's pretty much just how many times you can cut through. So Betty 2, how many times you can poke it and then you can open it up, right? It's because like Betty 2 encodes 2-dimensional hole. Betty 1 encodes 1-dimensional hole. Okay, so physically you can play around with that in such a way that you get to compute the Betty numbers actually. So it's pretty much interesting when you come to physically you can do something out of it and then compute the numbers, right? Okay, so Betty versus Euler characteristic. Again, they have a connection. They are related to each other. The Euler characteristic for a given object. So rather calling it an object, we call it as now manifold. Manifold in a global setting, it may look like Soviet, but in a local setting, if you like really go near to it, it will just look like as though like you are on a plane, just like a sphere. You can think of manifold as a sphere. An example of a manifold would be a sphere. We are on Earth, right? We are on Earth. At one point, we are now on Earth. At one point, we feel like we are on an Euclidean space on a plane. Yeah, at this point here, we feel like we are in a Euclidean space on a plane. We don't feel like, if I look far away, I don't feel like it's like curvy, right? The shape is not curvy. I don't see like the Earth is like curvy. I just get to see like it's all flat. That is the idea of manifold. Okay, manifold means locally it looks like you're on a plane. Okay, so for a given manifold, the Euler characteristic can be computed by doing or computing the alternating sum of the Betti number. Okay, the alternating sum of Betti number, I should write it here, equals to. Okay, that's how it is. So they are actually connected. So Euler number is like just one number, overall setting, whereas Betti, you get to calculate the number of connected components, you get to calculate the number of one-dimensional hole, two-dimensional hole, and etc. And then you can just like put them together. The alternating sum would be Euler characteristic. Okay, so the Euler characteristic of a torus is actually 0. Yeah, I showed previously 0. So how you can compute by just looking at Betti number, Betti 0 is 1, Betti 1 is negative, Betti 1 is 2, Betti 2 is 1. Okay, so if you get to calculate the connected component and number of holes, you would be able to do alternating sum and then compute its Euler characteristic as well. So what it means is that Betti number itself is actually, we can use that feature vector. You will see it later on. So that would be the first part of this lecture.